So I'll just begin. So let's see. So I'm going to start with what should be a 5 to 10 minute introduction on adults or something and so on. But one may argue it's a little pointless because if you haven't seen it before, it's not clear you can absorb it in 10 minutes. And maybe if you've seen it before, then again, it's probably redundant. But anyway, let me do it for the sake of completeness. So F is a number field. Right, so that's a finite extension of Q. You might as well think F equals Q. Okay. You have the places of F. So both finite and infinite. I'm going to denote them by P infinity and Pf. Right. So in the case of if F is Q, then of course this just means we have the place infinity and then 2, 3, 5 and so on. Okay, so that's what P is. So the adults, so we can do the following, right? So we define, so for each V in P, we define, so let FV be the completion, FV, and we form what's called the restricted direct product. So, okay, a couple of ways of doing this, which all amount to the same thing. So, the set as a set A will be a tuple with V in P such that XV is an OV for all but finitely many V in PF. Okay, so in other words, a typical element in this will, so what is OV? OV is of course the maximal compact ring of integers, which is the maximal compact subring of V. Right? So again, of course, if we are dealing with so what's the topology on this, right? So typically, a neighborhood base was 0, so zero looks like consists of sets of the form product. So consists of sets of the form product V in S, say UV, and product V not in S, OV. So what is UV? UV, so S is a finite set of places, right? Such that infinity and UV is going to be open set in F. So the reals, of course, or in the infinite places, there is no condition, right? There is this is only for V in PF, right? And so this is so with this topology. So of course, the point is AF becomes a locally compact ring, right? Okay. And the point is, so for example, you can also form the restricted, so yeah, so you can also form the restricted product removing the infinite place, and so that I will call A sub. So from now on, drop the subscript F, drop F, okay, so I'll just write A for the adults.
That V would be a neighborhood of 0?
Yeah. Oh, sorry. Continue. Okay. So the point is, if you just took the product, the line product, you wouldn't get something locally compact. But when you do this, you get a locally compact group, so you can do harmonic analysis, it's a hard measure, etc. Okay? One should note, oh yeah, so there's also this other thing. So, by the way, sometimes one writes this, one writes AF as the restricted notation is product over V of FV OV. So there's a compact set given at Albert finitely many places, and your elements must belong to that compact set at Albert finitely many places. So this is the notation. So you can also look at, so I'll just write A now, and you can also just forget the infinite place and take the restricted product, and that's called the finite index. Okay, so we not. Right, this is called the finite index. So this thing is of course the Adels, so those are finite index. Okay, so by the way, if you're familiar with the construction, you could also do the following. You could define AS to be, for a finite set of places, S to be the product V not in S, sorry, B in S, FV, and cross the product V, so maybe let's say SF, V not in S of OV, right? And then you could think simply of A as a, so this forms a directed system, and you can simply think of this as the direct limit S, yes, right? So that's another way of doing the same thing. Okay, so with this in mind, the first theorem one would like to state is, so there are some basic facts, which again I will review in 2 or 3 minutes, right? So first of all, F sits inside A diagonally, right? Right, so please send X to X, X, and so on. This embedding is closed, and okay, so maybe the first theorem or whatever. So this is closed. The image of F is closed in A, and so if you like theorem, if you've never seen it before, exercise, right? So F sits discretely, in fact, also. So F sits discretely. In A, and A by F is compact. Right? Okay. All right. And one, okay, so perhaps also in the same vein, one has, so let's just look at Q, for example. So F equals Q, and one has more or less as a consequence of these ideas, the fact that Q plus R plus KF is nothing but A. So maybe first, I'll say Q plus F, sorry, not Q, Q plus KF is nothing but the finite adder. What is KF? It's a product with ZP over all primes, which you can also think of as Z hat, right? And alright, and therefore also Q plus KF plus R is nothing but the adders. And what this allows us to point out, so now if you quotient by Q, you can see. So obviously, if you look at A by Q, so notice that Q is sitting diagonally, of course. So the intersection of Q with KF is exactly Z. Alright. So when you take A by Q, right, and in fact also if you like quotient out by Z hat, you get exactly R by Z. Okay. So this perhaps, so after all, Sandeep's lectures yesterday started with Fourier analysis on the circle S1, which is R by Z, and so this adelic this space A by Q is kind of some kind of analog, which is in fact compact, but also has extra information at the finite primes sitting inside. Okay, so this is kind of by way of motivation, I guess. Okay. So we will be looking at, so the Adels form a ring, so of course one can look at GLN A, okay. It can also be thought of as the restricted product of GLN FB KV, right? So at all but finitely many places, the elements will belong to KV. What is KV? KV is of course GLN O. Alright. And that's a maximal compact subgroup at all the finite places. V finite. Right? So if you have a, we are actually going to view this as sitting inside as a closed subgroup inside some larger SLN. Right? In fact, we may as well take n, capital N to be 2n, and by sending G to G transpose G. So this is actually, yeah.
So it, A mod Q itself is compact, right?
Yeah, M mod Q is compact, yeah.
But shouldn't the I mod Q cross the...
No. That's something else.
No, like, see, Z, you had quotiented R over Z. Right?
Yeah.
So, how are you?
No, Q intersection Z hat is exactly Z, no? This is additive notation, not multiplicative. I mean, that's another statement. The fact that I1 mod K star is compact and so on, that's another statement. That's a multiplicative version and that's much harder. Okay, much harder, yeah, hard, definitely hard. Yeah. So, anyway, so this is how we're going to view GLNA. It will be sitting inside this. And we have a natural, so first of all, on the Adels, we have the notion, we have a norm, so if X is in A, right? You can, at each place, so X is XV, right? It's a tuple, infinite tuple. And so we can define the Vth norm of X to be the Vth norm at the, of XV. Okay, so you take the Vth component and take its absolute value, so that, and then if you take the product of these things, you get the adelic norm. Okay, that's a definition. Right? And one of course checks that, for instance, elements in F will of course have norm 1, that's a product formula of Artin. And but we can use this to give a norm on GLN. So if G is in GLN, then we can define the norm as follows. So the norm of, so first of all, norm of GV will be defined as, or the Vth norm, so let's see, GV will be defined as the sup of Gij. Well, my notation is not great notation, but I have put these inside and outside. Gijv, okay, and G inverse Ijv, V, right, sup over Ig. Okay, so basically we are putting a norm on this, on SLNA, the usual norm, but you know, you're restricting it to this GLNA sitting like this, and this is what you get. Okay. So in the literature, it's slightly more common to use the L2 or the Hilbert-Schmidt norm, but this is just as good, this is a sup norm. Oh, sorry, this will be, and of course, the norm of G will just be the product over V of all the individual. And of course, it's an exercise to check that most of these things are 1, so of course the product makes perfect sense. Right? So all but finitely many will be 1, so you can easily check that. Okay, so this is a norm that we put on, okay. And as before, so GLNF embed diagonally in GLNA, and again it's discrete just because F inside A was discrete, and so you can look at the quotient GLNA by GLNF. So for instance, if N was 1, then we would be in the setting of the IDELs, which is what you wanted. And yeah, okay, so of course, again, there's a hard measure here, and this is that is sitting inside, so you'll get a measure on the quotient space, and varied measure on the quotient space, GLNA by GLNF. Okay, so get varied measure on quotient. Right? And using, strong approximation for F, or one gets what's called weak approximation. So if I have any, so let's, this is perhaps so theorem 1 maybe, that's an exercise, so it doesn't count. So we have the following theorem. So there is, I guess, yeah, anyway, so oh, I need some more notation, which I should fix, so before that. So let's put some notation in. So I want to stop writing GLN because N is always 6. I'm just going to call it G. So G is equal to GLN. Okay. So I'm going to have G infinity will just be the product of the groups GV, V dividing infinity, and GF will be simply restrict GLN AF. So GAF. Okay. Which of course is product, restricted product V of GV, V not dividing infinity. Alright. I'll also need the maximal compact groups, let's say K infinity and KF. So yeah, so in particular notice that G is nothing but G infinity cross GF, right? And we also have maximal compact subgroups. So you have K infinity, which will be the product of the KVs at V dividing infinity, and we have KF, which will be the product of the compact groups KV, V not dividing infinity. Okay. Alright. So all of this just to set up my basic notation. And yeah, okay. So there exists, so theorem. One, there exists finitely many elements Ci in GF such that, so it's kind of analogous to where was that? Yeah, this such that GLN GA equals GF times G infinity times Ci times for any, so I should this, so for any open compact subgroup Kf prime of Kf. So Kf is a compact open subgroup. I am taking Kf prime inside Kf. Okay. So this is something we need to use repeatedly. It basically assures us that, so again using the same set of ideas, right? So again, what happens if F is Q, for example? Right? So suppose F is Q. Right? Then there's of course only one infinite place, and in that case, by the way, the finitely many Ci's, I wrote equals, so I put union, I equals 1 through R. My apologies. So GA is the union of these finitely many double cosets, but when F equals Q, in fact there will be just one, and I'll end up getting GA is nothing but GQ times GR And let's take k prime to be equal to k. So then it just be product GLN ZP. Okay. All right. And once again, if you do yeah. So once again, if you take if you quotient if you quotient this by GQ, right? You'll end up, you can actually right. So let's do it like this. Sorry,
G capital F.
can't hear.
G capital F.
G capital F. Where?
In the union.
What is this you're asking? GLNF. Yeah, just like your. Okay. So the point is when you quotient. So notice that if you intersect GQ with the product of this is again sitting diagonally. So if you intersect it with the product GLN ZP, right? This is nothing but GLNZ. Okay. So basically, GA by GQ looks like GLNR by GLNZ. Actually, it looks like, okay, if you looks like GLNR plus by center times SLNZ, but okay, roughly speaking, that's the quotient you're interested in.
CI belongs to GF or it belongs to GAF?
Oh! Yeah, okay. Yeah, sorry, now I understand that. GF. Small. Apologies. Yeah, maybe that is the question, sorry. Okay, so those are the preliminaries, and now we can get down to actually the subject matter for the talk. Okay, not doing so badly. And so we can now define, we have all the preliminaries, which I will now do. Okay. So what do we need? Very good. Alright, so if I have, since I have GA, I've written it as a product like this, right? So G is in here, I'll write it as some product G infinity times GF, right? And with this notation, so now a function f from GA to C is said to be smooth if the following, if 1, f is continuous, okay. 2, for each fixed GF, the function G infinity goes to f G infinity GF. This is C infinity, right? So this is a function on the real group, so smoothness makes perfect sense. And finally, for each fixed G infinity, the map GF goes to FG infinity GF is a locally constant function with compact support. So this is a locally
Sir.
Yeah.
So this is true for p is less than infinity, or p
Is it true for what?
is less than infinity, or it is true for every p? This product,
Which is what true?
this product of GL and ZP.
This.
No, ever.
Oh, this is P finite, of course. I mean, GL and ZP have no meaning if P is not finite. Okay, so this is what it means for a function to be smooth. A function on GA from GA to C to be smooth. Right? It must be continuous. It must be smooth in the infinite variables, and it should be locally constant with compact support. It's a locally constant function, not compact. Locally constant function with compact support. With compact support in the other finite cases. Okay, all right. So now we can define an automorphic form. So what's an automorphic form? Maybe we can get center stage. Finish that. So an automorphic form is going to be a smooth function, of course, which is why we defined it. Okay. So let's see. So a smooth function let's say phi from G A to C is called an automorphic form. If the following conditions are satisfied. So one, phi gamma G equals phi G. So it is GF invariant on the left for all gamma in GF and GA. It's for so what do I want? K finiteness first or Z finiteness? Let me just okay. So phi is K finite on the right. So what does this mean, right? So for I look at the span of phi gk, as k varies. So if I let b not be the span of phi kg, kk, right? So what is phi kg? Phi kg is just phi gk. So this means, sorry, then I demand that dimension of b naught be less than infinity. So that's one condition. Another condition is that phi is zg finite. So you have the action of phi is a smooth function in the infinite at the infinite places. So you have a action of the universal enveloping algebra and its center. So and you demand that phi be zg finite. Okay, and 4, phi is of moderate growth. So yeah. So there exists Cm greater than 0 such that so this is, yeah.
Dimension of B naught.
Sorry? So this is the center of the universal enveloping algebra, which has, I think, certainly made its appearance before. And I'm saying phi should be Zg finite. There's an action of the center of universal enveloping algebra on phi. And that's, again, the Zg span of these functions should be a finite dimensional vector space. Right? So that's what Zg finite means. Okay. So I guess this certainly came up in Narayan's lecture yesterday at equal at some point. Anyway, okay. So this is what it means. Yeah. Oh, yeah, of course. Rho G. Yeah. So this is a finite. This is the moderate growth condition, right? So this is left GF invariance. So it's invariant on the left by discrete group, in fact by GF. It must be K finite. So the set of K translates on the right form a finite dimensional vector space. The set of ZG, it is ZG finite. So again, the span of ZG acting on phi is a finite dimensional vector space. And finally, there must exist constant Cm such that this growth condition is satisfied. So this is sometimes called moderate growth. So automorphic forms are functions which have moderate growth. Alright. So now,
Does it?
yeah.
Dimension of V naught over which field?
Sorry?
Dimension of V naught over which field? F?
Over what? Sorry? No, these are complex vector spaces. What was the question?
The question was, what is the underlying P for V?
What was?
The underlying P for V.
Yeah. I mean, this is a space of functions, right? Complex valued functions. Phi is from GA to C. Yeah. So, if I'm talking about a vector space of functions, that obviously the underlying space is going to be C, right? Okay. Okay, so now, so V naught is finite dimensional, and there are going to be certain representations that occur. So V naught, we know the dimension V0 is finite dimensional, right? So it must break up. K is a compact group, so we can write V equals a direct sum of some representations. P pi, pi in some set. So theta will be a set of irreducible representations. The set of irreducible representations that occur in the decomposition of V0 into irreducible representations. Irreducible representations. Okay. And because it is ZG finite, it must of course be annihilated by an ideal of finite codimension in ZG. So there will be some ideal. Also, there is an ideal. Let's call it J. A finite codimension. That annihilates such that G phi is 0. Right? Yeah. Sorry, what?
We
Want a character?
the uniform we should be having this common down for like we should have D phi. The D is
So that might probably follow from this.
No.
why would G phi, K phi?
No, that follows away because, okay, I'll come to that. That's a comment that we made. Okay, yeah. Shortly. That's follows from, I guess, Harish Chandra's lemma or something, right? Because phi is anyway can be written as phi convolution F, where F has compact support, and then etc. So, okay. So, right? So, basically, attached to this automorphic form is data. These two pieces of data, theta, which is a set of irreducible representations of K, and J, which is the ideal of finite codimension in ZG. So, this will be called, so this pair, so phi is an automorphic form. Right, J, right? And so then, here's the main theorem, if you like, that, or one of the two main theorems that we will try and prove. So, for that, so let AJ theta be a space of automorphic forms. of so then the theorem, which is both Harishchandra's, is the dimension of AJ. Fine. So the space of automorphic forms corresponding to a fixed J theta is a finite dimensional space. So that's the theorem of Harishchandra's, and that's one of the two theorems that we will try to prove in the next few lectures. Okay, so this is the main thing. Okay, so today I'll try to.
Ravi, just to clarify, capital T stands for K of times K infinity.
Right.
It is both product of finite and
Finite and infinite. Yeah, you can, of course, I could have just kept K infinity and done the thing with K infinity, but you can also do it like this. In my notation, K is K infinity times Kf. Right, so maybe, see, so there should have been a line below this, but that's what it is. So maybe I should keep this notation actually on the board for what it's worth. Okay, so I just. Okay, so how does one prove this theorem? So the strategy will be the following. Yeah, we will first define another subspace. So I'll give you examples of automorphic forms in a couple of minutes, but the strategy is going to be the following. So define another subspace.
Ravi,
Sorry?
so theta is a fixed subset of irreducible.
Theta is exactly the set of representations that occur in the decomposition of V0 into irreducible representations of K.
Yeah, but when you are writing A of type J theta,
The theta is fixed. You fix your theta, you fix a set, okay, sorry. You fix a set of irreducible representations of K and J, and you look at automorphic forms of type J theta. So, okay, theta prime if you like.
theta is one reducible, right?
Finite set of irreducible representations. So let's say theta prime and theta prime. So this theta prime has nothing to do with that.
Theta representation of K.
K. Theta is a set of representations of K. Finite set of representations. Yeah, finite because V0 is finite. Yeah, okay. Okay. Alright. So then I should leave this as theta and maybe call that theta. Yeah, but it still doesn't solve the problem. Okay, theta is fine. Okay. So the strategy, such as it is, problem? No. So is we'll define inside T. We'll have another space which we call A0 J theta, which will be the space of plus forms. Okay. This will sit there. Yeah. And we will prove that this space is finite dimensional, and then there's an inductive argument which allows you to conclude that the space of all automorphic forms is finite dimensional. Okay? So the reason it's easier to prove that this space is finite dimensional is that elements of this space will actually end up being bounded functions. Okay? And okay, that may not be by itself, that doesn't say anything, but there's a small lemma which I will now state. So the point is A naught J theta consists of essentially bounded functions. So L infinity norm. Actually, finally, they consist of bounded functions anyway. So essentially, bounded just means that the sup norm is finite. Okay, and the reason that's good is that we have the following lemma. And by the way, they will also be they will also lie in L2. In L2 of something, okay, let's say, okay, I have to also lie in a suitable L2, in L2 of something, a space which I will tell you about shortly, okay, and when you have this setup, one has the following lemma, which allows
In your relation, here you are saying that V naught would be decomposed. V naught will be decomposed to the representations of T. Right? And that is parameterized by theta prime.
theta prime, yes. So now I just take, so I'm telling you what an automorphic form of type J theta is.
Oh, so now you're
This is fine. So this is what it means. So I'm saying associated to any automorphic form, there are two pieces of data, J and theta prime now, right? So then such a phi is said to be of type J theta prime.
theta prime.
That's theta prime. Now here I'm taking some finite set theta and some, well actually I should take J prime too. Okay. Right? Some other ideal J prime of finite codimension ZG, and I'm saying, look, I will call my notation AJ prime theta prime is a space of automorphic forms of type J prime theta prime. And then I'm saying that dimension that is finite. Yeah, I hope there's no further confusion on this. I'm just saying that there's a certain two natural pieces of data attached to a form, and I'm calling that form then of type J theta. And then I'm saying, look at any kind of data J comma theta where J is a ideal finite codimension and theta is a set of finite set of irreducible representations, and then all forms of that type are called the space of all such forms is denoted A J prime theta prime. Okay, that's okay. So inside that we're going to have another set. So inside AJ theta, we're going to have another set of plus forms, and those will consist, as it turns out, about it. And in some sense, much of the work in these lectures will go to proving this statement, that there is this subspace which I have yet to define, although it's kind of made a cameo appearance already in Sandeep's lectures. There were cusp forms there, and that's what these will be. Okay, so maybe I'll just state the lemma. Maybe we prove it because it's sometimes attributed to Godma, though my functional analyst friends tell me that people had observed it before. So let X be a locally compact space, I guess. Space and with some measure mu, Borel measure mu, such that mu x is less than infinity. Okay, suppose V is a so N2x is of course with respect to the measure mu. So suppose V is a subspace, is a closed subspace. Consisting of, and if f is in V, then f is essentially bounded. So sup norm of f is finite. Okay. Then V must be finite. Necessarily finite. Okay, so if you have a closed subspace of L2 consisting of essentially bounded functions, then in fact that space must be finite dimension. Okay, so maybe I'll give a proof. There aren't that many things I can prove, so I might as well prove this. Okay. Alright. So note one thing, that of course if I have f, then the L2 norm is, I guess, bounded by a suitable constant times the sup norm. So suppose L infinity, so the L infinity norm, right? So I have a map, let's see, so which ways? So I have integral d mu on x is of course less than or equal to m times m squared times mu of x, I guess. If m is the if. Right? So this shows you that the L2 norm is bounded by the sup norm. It also said that if Fn goes to F in the sup norm, it automatically goes to F in the L2 norm, so these also close in L infinity. Right? Okay, so now you can look at the identity map from V to V, right? Going from the F2. So this was going from L infinity. So think of this as being closed in L infinity, this as being closed in L2, right? So it's going from V to V. This is the identity map. It is obviously bounded. So by the, and of course it's bijective on V, it's the identity map. So by the open mapping theorem, the inverse is also continuous. So open mapping theorem says the inverse is continuous, which means that the L infinity norm is bounded by the L2 norm up to some constant. So it implies it's not equal to something, C times 2 or something in K. Right? So open mapping will tell me that. And now let's just take so let's take and also let E1. So I want to prove that the space is finite dimensional. I'll just show that any orthonormal set of vectors, the number of them has to be bounded by some fixed thing. So let E1x, Enx be orthonormal functions, right, in L2. Then what we, and let's look at this functions Ci, Eix for some constants. Let's say, sorry, in V, in V of course. We're trying to prove that V is finite dimensional, so we want to say that.
In your statement of the lemma, we are assuming that second entity is less than infinity, or is that something which is getting implied?
Sorry? No, it's an assumption.
If F belongs to it, then second entity is
The close of, and if F, no. Suppose, let x blah 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 blah. Suppose this is a closed surface, and suppose this.
and not
Yeah.
that.
And if F in V, then no. And
And for.
okay, and for okay.
For.
Thanks. Okay. So is that clear now? Okay. Good. So let's look at this. Obviously, this is less than the sup norm of this function, whatever that is, and the sup norm or infinity norm of this function is less than the L2 norm, and the L2 norm of this function is just summation Ci square raised to a half, right? So times, okay, so this is less than, okay, Ci Eix infinity, and that is less than say, K times summation Ci square that's the L2 norm of this function after all. And now just take Ci to be, so this is for a fixed x. So take Ci to be Ei x bar. Right? So if you do that, then you get summation Ci Eix square, and on that side, you see you get less than K times summation Eix square to the half. sorry, there's something. There's no Ci here. So I've taken Ci to be this. Just substitute there. Summation absolute value of Eix square is less than that. But now, of course, you can essentially cancel off one factor. So you're getting a bound like summation I equals 1 through n Eix square to the half is less than or equal to. Now integrate over x. These are orthonormal functions, so you're just going to get n. So integrating on x will give you n is less than k times mu of x. Over x. In x, the measure is finite, so we're just going to get n less than or equal to k times n or n squared. Oh yeah, so I want to square this. So maybe I say this. That's true. So I want the square. So I want the square of this, not the square root. So look at this function. It's less than or equal to k square. Integrate over x, and I will get n on the one hand, or on the other hand, I'll get use kx.
Right? Ci.
Sorry, this I took Ci to be Ei of x. X is fixed. Fix x. Now integrate over x after. Yeah. Yeah.
That bound is independent of f, right? Like that.
Which this one?
Yeah.
No. Why should it be? No.
Because
It's not. It's just you just want to say that the 2 norm is less than. Oh, this is the wrong way. Maybe. This m may be the wrong thing. What a better. I think I may have written this the wrong way. I don't think I want m here. I just want to say that. Sorry, this was not m. This was mu x or something. Apologies. Thank you. Sorry. The bound, I wrote m instead of mu x to the half, that's a correct no. That's a no. Okay, so anyway, so there it is. N is, so if you had a space, so what we're going to prove is that A naught J theta will be a closed subspace of an appropriate L2 consisting entirely of bounded functions, and then Godman's lemma, which will tell you that n is less than the dimension of the space is finite dimension. Okay, so this is a basic strategy of the proof. By the way, this particular proof is apparently due to Hermander. It's a particularly slick proof, and I got it from Borel's SN2R. Okay, so in the remaining 7 minutes, I will just give you a couple of examples of automorphic forms and maybe make a couple of reductions, if I can, before any time. So let me just make a remark. Finally, the problem is, you have to say something is essentially bounded or something like that, right? And that will involve understanding this moderate growth condition. Now, the moderate growth condition is saying something about absolute value of phi of g for all g in GA. And that's kind of annoying to verify at the level of the group. So on the other hand, these are functions which are GF invariant. So really they are functions on GA by GF. And what we will do is to say that there is a nice subset of, there are several nice subsets, they call Siegel sets or Siegel domains that sit inside GA, and it will be enough to estimate the functions on these subsets. Okay, so finally we'll have to describe Siegel domains or Siegel sets and do some counting of lattice points in that domain and so on to get the relevant estimates. Okay, so just examples. By the way, of course, all of you have seen examples of automorphic forms. So when n equals 1, what happens? Well, an automorphic form looks like this. So when n equals 1, the moderate growth condition turns out to be redundant. And what does an automorphic form look like? It looks like phi of g will look like summation j equals 1 through say r chi j of pj of log. So let's say x, because now it's just here. Okay, So what are these terms? So Tj is just a polynomial. Oh, I'm missing. No, that's it. So here Tj is a polynomial. So I have a polynomial in log mod x. And chi j is an ideal class character. So that's a character of GL1 with A, which is trivial on GL1F. For those of you who never seen this before, Dirichlet characters, for example, naturally give me ideal class characters when the field is Q. Okay, so this is what any automorphic form on GL1 looks like. Yeah, just basically sums of ideal class characters, but with this extra term thrown in with Pj log mod x. So when we have n equals 2, we saw some examples in Sandeep's talk yesterday. So you can start with a mass form, right? So let's give a name. Let psi be a mass form. As in Sandeep's talk. So what does that mean? So a mass form yesterday was on the full modular group, right? Did you take? Yeah, you took the full modular group, right? So that means it was invariant under SL2Z on the left, right? So what we had was a function on the upper half plane which was invariant by SL2Z on the left, but the upper half plane of course is nothing but SL2R by SO2 and so on, right? So what you can do, you can get an automorphic form because of the approximation theorem, which I unfortunately erased. Let me just do what have I called it? Psi? Yeah, psi is good. Okay. So one can define phi psi. Basically, I can define, so I have, so let's take, so here now the field is Q, okay? So these mass forms are automorphic forms over Q, and over Q we have the decomposition of the adels into GF times G infinity times compact subgroup, right? I will simply define this to be psi of G infinity. Okay, this makes sense because this G infinity is living in GL2R plus or something, and GL2R plus acts on the upper half, so maybe very explicitly G infinity I, right? So G infinity lies in, say, GL2R plus this acts on the upper half plane. In particular, it says I somewhere. That's what we call usually the variable Z, right? So this will be psi of Z in the classical language, okay? And the fact that it is this mass form is left invariant by SL2Z will tell me that this is perfectly well defined, because again the intersection of whatever relevant intersection of what GL2Q intersect something will be SL2Z times Z infinity over. Okay, so you can easily check this condition given a mass form, classical mass form. One can do this. In general, so this was what is called a mass form of weight 0. There are mass forms of other weights, and there are also holomorphic modular forms. And there you will, the thing will not be right invariant under Kf, but only under a compact open subgroup of Kf. Okay, so in that case, you may have more cosets, etc. To deal with, and well, not over Q, but over general fields you may have more double cosets to deal with. But nonetheless, this is how classical automorphic forms give rise to adelic automorphic forms. Okay, I think I'll say one more thing before stopping. Oh yeah, so when n is, let me just make this last definition, and okay, now I can erase this. So when n is greater than or equal to 2, right? Oh no, I need this definition. So let me define the following object, not object, but sorry. Okay, so let's. This thing will be y adels So y will of course look like some t comma t comma t. So I'm telling you what this subgroup of the ideals is. T in R greater than 0. So let's look at all ideals of this form. You simply have the same T sitting at all the Archimedean places, and at the non-Archimedean places, it's simply 1. Okay, so you call that A cross greater than 0, and let Z greater than 0 be the elements of the center, that is your diagonal matrices. Okay, so actually you can identify any element here with, of course, an element y in A cross. So anyway, it's just not diagonal, just scalar matrices, right? And what one says, if n is greater than or equal to 2, so anyway, phi is going to be ZA finite. Okay, so the fact is that if you have any automorphic form, you always have phi Z G equals summation mod Z to the lambda J. You can always write it as a linear combination of things like this. Pj of log Z log mod Z times phi Z. Okay, for Z in the Z greater than 0 and G in GA. Okay, so what I'm getting at here is basically I can write everything as I can basically think of my automorphic forms as Z greater than 0 finite things. Okay, so I can only look at those, and further by modifying my automorphic form by power of the determinant, I can actually assume that there is Z greater than 0 invariant. Okay, so bottom line is I will now okay, so I'm done anyway, so maybe I can write it just here. So we'll assume, essentially without loss of generality for whatever it is that I want to do, that phi of Zg is just phi G for all Z in Z. So under this subgroup, I'm going to assume that my forms are actually invariant. So I'll just stop here, right? My time is up.